atoms bump into each other in a bar and have a fight, and one of them loses an electron. And the first one says, "Are you okay?" And the second one says, "Yeah, I'm okay." And he says, "Are you sure?" He says, "I'm positive." Dr. Ray. Dr. Lackey.
Oh.
Our own resident physicist, Duane Ray, continues his series on scientific perceptions of the world around us. Having offered an explanation of the Big Bang Theory and an analysis of the pseudoscience behind creationism, Dr. Ray will speak today on quantum mechanics and relativity. Those of us who have heard him speak before are familiar with his professional background. Therefore, I ask him to share something on the human interest side. Just as our friends Del and Carol Lee Allen, Duane and his wife Gisela built and live in a concrete house, but possibly for different reasons. Duane liked the idea of building his own house, but in his words, "I'm in the woodworking category of I cut it 3 times to fit and it's still too short." He can, however, stack Lego blocks and squirt concrete in them. Gisela placed the tile on the concrete floors, and Duane says if they drop anything on those floors, they don't pick it up. They just sweep the broken pieces together. See it for yourself. This is an actual picture of the house, and my guess is you will probably have some questions about that after the meeting. A PhD from the University of Pennsylvania, Duane's physics credentials outrank his woodworking ones. So let's hear what he has to say about quantum mechanics. A welcoming hand for Dr. Duane Ray.
Thanks for that great introduction. And I don't know if how many of you were at the potluck last night, but out at Del's house, another concrete house. And actually, you can't tell that it's a concrete house because it's all covered over with things. But the design that he and his wife put together is a gorgeous, wonderful, beautiful house. A lot of heavy beams of wood and so on. Just a pleasure to see and enjoy. And there was some great music last night too, so I recommend those potluck. Another reason I was there was because my wife is away and she's going to come back later this week. She's been gone for 3 weeks. It was the best good meal I've had in a while. Not a cook. Thanks very much for the opportunity to speak about science. Whenever we have a vice presidential candidate that's a creationist, that's a serious person involved in politics now, it's really kind of great science. I'm sure you guys still like it. So science is so important. And let me get started. I'm going to talk about relativity, and then I'm going to talk about quantum mechanics, and maybe we can take a break in between and have just maybe a couple of questions, 2 questions on relativity, and then at the end we'll talk about quantum mechanics or whatever else. So we can go that route. First of all, especially on a Sunday morning, let me put out my disclaimer. As Ziggy found when he went to the top of the mountain to the Google, this is the facts of life. The meaning of life is 2 mountaintops over. So I'm not going to talk about any of that stuff. But we are going to explore some new ideas. We're probably going to fall off some cliffs, but that's okay. I don't understand a lot of this stuff myself, but it's fun to talk about. There's a lot of interesting things that you can concern yourself with and think about, and do kind of make sense after a while. One of the problems with this material, though, is that you find that analogies in our real world, in our apparent world, don't always convey well the ideas of the real world, relativity and quantum mechanics. So you can't go too far down a direction without coming back and rethinking, and maybe you need a different analogy to make that work. I have no idea why it's doing that thing by itself, but it is. Anyhow, this is what I wanted to talk about. My view is that science is neither a method nor a body of knowledge. It's a body of changing learned opinion aspiring to be true. There are certain facts about nature and history, and our grasp of those facts is constantly changing. We don't know all the answers, but we know a lot of them, and we're really very good. So we're getting closer and closer, but we don't know the answers, and we know that we don't know the answers, so it's fun to work at getting more depth. And we'll go into some of the details about why we're getting closer and how close we're really getting to it. I just mentioned it's hard to give accurate analogies. That's basically what that says. And I want to remind you that whenever we're looking into the outside world around us, the universe around us, basically all the information we get comes to us through chunks of energy called photons. They travel at the speed of light, have no mass, and they convey a tremendous amount of information. Photons are electromagnetic chunks of energy. Light is made up of lots and lots of these photons. Some of them are red, green, blue, yellow, all the colors, different wavelengths, different amounts of energy. And then there's some other photons that are X-rays or gamma rays, shorter wavelengths, more energy. And then there's some that are ultraviolet. There's some that are infrared, radio waves, longer wavelengths, less energy. But they all give us some information about where they came from, and that gives us tremendous ability to explore what's out there. Since we understand very well the interaction of photons with atoms, we know that the atoms out there are exactly the same as the atoms here on Earth. If we explore this a little bit further, we can measure photons very carefully, and we can tell whether that gas it came from is moving away from us or toward us, and how fast. So we get a tremendous amount of information. Oh, some meteors drop in and we get some rocks out there, and we go to the moon and pick up a few rocks. But overwhelmingly, the amount of stuff we get is from these photons that come to us, and we'll talk a lot about photons here in the next little bit. This is a guy who is probably one of two geniuses that are stand head and shoulders above everybody else. Newton was the guy a couple of centuries earlier, and Einstein was just an amazing person. He had a really magnificent year in 1905, and he explained the photoelectric effect, which basically quantized these photons, these energy. It said it's only chunks of energy of a certain amount. And he got his Nobel Prize for that. That was published in March. He explained Brownian motion, which was a big conundrum for people. They didn't really understand. They saw these little things jiggling around under the microscope, but they didn't understand why. He did that in May as just a throw off from his thesis work. And then space-time relativity, he published in June. And size of atoms and molecules, he finally got around to finishing his doctoral thesis. He had a lot of things going on. And then, as a result of the space-time relativity, if you do look from a couple of different, we'll talk about different people moving past each other at different speeds. If you look at a billiard table and you see how the balls interact and bounce from one another, and you look at from two different time frames, two different uniformly moving things, that requires that you come up with E equals mc squared. So that's all from special relativity before you get to general relativity or anything like that. Tremendous year. And this is a guy that his professor said, lazy dog. Couldn't get a job. And he ended up working in a patent office because he couldn't get a job anyplace else. And let me make one other comment here, so I don't forget it. Space-time relativity, if he hadn't come up with that, within a couple of years, science goes along and there's a time that's right. And we find that for a lot of things, for instance, we found it in the West, and although we didn't know it because of the Cold War and the Iron Curtain, they found it in Russia at the same time, or similar times. And that's probably true. If he hadn't done it, somebody would have come up with it in a few years. General relativity is another whole bag. That's really off the wall, and it probably would have been a decade or two before somebody would come up with that, certainly with as clean a presentation and analysis of looking at it. Okay, well, we really know that this is not totally correct, either quantum mechanics or general relativity, but we know that it's not correct to a really fine accuracy, okay? So we know a lot about it, and that's why all your cell phones, all your GPSs, all that kind of thing actually work. There's a difference between fact and fiction. Fiction has to be believable. I'm not going to lie to you, but I'm going to tell you a lot of things that you're probably not going to want to believe. But that's okay. Alice in Wonderland didn't believe that either, and she said, I can't believe that. Can't you, the Queen said in pitying tone. Try again, draw a long, deep breath, and shut your eyes. Alice laughed. There's no use trying, she said. One can't believe impossible things. I dare say you haven't had much practice, said the Queen. So I implore you, practice, practice, practice. I'll keep coming back to that. Okay, special relativity. This is the earliest part and the rather more, actually a little more complicated when you try to think things through because there's some good analogies for the other. But relativity means that somebody is moving at a uniform rate compared to somebody else. And of course that means that you're moving with respect to them. It depends which place you're looking at. So if we're standing on a station platform and there's a train coach going past, and suppose there's somebody in the train coach and he has a ball, and this is what we've experienced maybe with a kid or something like that, and he throws the ball at 20 miles an hour and it's moving 45, we know that that ball compared to us is going 45 miles an hour plus 20 miles an hour, 60 miles an hour.
65.
Okay. I know you're not sleeping. I have people pick up spelling on these things all the time too. Well, I guess I blew the rest of the talk. Okay. So anyhow, this is the kind of thing I better get so anyhow, that's what our normal thing is whenever we view these things. But if you say that that ball, instead of being a ball, is a photon of light, always goes at the velocity of light, which we call c, at the same time, and whether you're looking at him or he's looking at you, it's always that speed. So it doesn't add on to his speed. And that's the conundrum we're going to be working with. Here's another way to look at things. If in the atmosphere, around here with all the air and so on, we have a train going past, and they blow a whistle, we know that because he's moving in this direction, the waves of sound that are generated tend to be compressed, because this one is emitted before this one has a chance to move very far away, and it's further away from the one back here. So here you have longer wavelengths, here you have shorter wavelengths, so you tend to have a high pitch coming toward you, and then as a train goes past you, or the race car goes away from you, the pitch lower. So it's that kind of thing. We're all kind of familiar with that sort of stuff. Okay, well, people back trying to understand about light figured, well, the Earth is going around the sun, and we know that it's going about 67,000 miles an hour. We know the speed of light is about 186,000 miles per second, but we have enough resolution in our experiments that we can measure that and find out. And we would expect that in one case it subtracts off, and in the other case it adds to it, depending whether you're going for or against. And this luminiferous ether, everything has to be transmitted on something. Sound is air and so on. Waves are in water. So they seem to think that light had to trail on something. Now, it moves very fast, so whatever it's traveling on has to be really rigid. And we'll find that space is really rigid. But if it's rigid, how can the Earth go sliding through it so effortlessly? That was a real problem. So anyhow, they wanted to measure this, and what they found, the Michelson-Morley experiment back in the 1880s, they found no difference. They couldn't see this, so they were really confused now at this point. And that's one of the things also that helped Einstein understand his special relativity. So here's somebody standing on a station, and here's somebody moving along, and what they each observe is like this. You have a splash of light, flash bulb or something goes off there, and the person in here sees that the light is going to go just straight up, and then it's going to turn around and come straight back down, and the person on the platform sees him moving along, and he sees the light ray move up like this. And actually, this hypotenuse and this triangle can give you the conversion between the times and distances and stuff, but we won't go into that. So then it comes over here, and this person says the velocity of light is c, and this person says the velocity of light is c, but it's gone a lot further for this fellow than it did for that. So how do you explain that? And that's, of course, the real question. And Einstein had the insight. And what it really means when you go through all the equations and so on is that the person moving along here looks shorter to him. And it turns out that his clocks are also going to be running slower. And, of course, it's totally symmetrical. So everything has to be consistent with that kind of symmetry. And, for instance, one would expect if you have a light that goes pop here, then the light waves move out in a direction in a similar circular way. And if something were moving, you might expect the light waves would have a similar kind of thing, just like the water waves in a boat going forward, or the sound, whistle sound waves, like I said on the train before. But in fact, what really happens is something like this. They're all narrower, everything is squeezed together, and it's only along the direction of motion, it's not perpendicular. And what happens is a combination of the thing that's moving with respect to you looks both shorter and the time is slower, the clocks are slower. So here it's 5 o'clock, it's only moved to 2 o'clock on this one. And that's consistent and that works real well. And let me give you an example that really is kind of bothersome. If, for instance, this is the twins paradox, where you have identical twins, and one's going to get on a spaceship and one's going to stay on Earth. So on Earth, one twin, and the other one gets into a spaceship, and they're going to accelerate at 1 gravity, so it's comfortable. They can't tell whether they're on Earth or not because you arrange the acceleration of the spaceship, so it gets going very fast, very quickly. And he goes along, and at the middle of the distance, going to the middle of our galaxy, 30,000 light years away, you turn around, and now you're going to slow up, okay, as you get closer to this, so that you could turn around and come back or something if you wanted to. But you arrange it so you're going with 1g now pointed in the other direction as you slow down. Well, since this guy has moved up, and 1g for 30,000, 15,000 years gets you up to a really good speed. So what that means is that after a while, you have one twin over here on Earth, the other twin at the center of our galaxy in a spaceship, and it turns out that only 20 years has passed on the spaceship, and 30,102 years have passed. It's 30,000 light years, okay? He's going less than the speed of light, so it takes a little bit longer than 30,100 years, 102 years. And if he were to turn around and come back, he would have found that his twin brother is dead for 60,000 years. Strange but true. It really is what happens, folks. And because we don't see things working at these kinds of speeds, we really don't notice those things as we're moving along. And one of the things I did bring along, and I only have 50 of these, but with this number of people that are here, this is a handout, and you can take them home. Next week there will be a test on this. You can pass them on. This gives an idea of, depending on how fast they go, compared to the speed of light, how much the mass changes, how much the speed changes, and how much the width changes. And you'll find you have to be going half the speed of light before you start noticing a couple of % difference in these things. So it really does make very little difference here at our I can't believe that. Practice, practice, practice. Okay. We see an intermingling of time and space. And from conservation of momentum, as I mentioned, we go up to this E equals mc squared, which is probably a well-known formula for just about everybody. This is something that shows up. And of course, that's why atomic bombs and hydrogen bombs work and so on. And they really are equivalent. You can convert one from the other in various techniques or ways. And if you put a certain amount of energy into empty space, it's possible to create particles. So all kinds of neat things can be happening. One of the things that you might say before we go on to the others is that if I'm moving through space and the time is getting shorter, if somebody is moving through my space, he's trading off and not using as much of my time. Okay, and of course it works the other way around also. So there's an intimate connection between space and time, and you can trade off one for the other. And that's what happens. That's sort of one way to look at some of these things. A lot of these things come up basically just from looking at formulas and trying to interpret and understand. And I wanted to throw this in to give you a sense of how really important and how powerful the insight is from a lot of the logic of mathematics that comes out. And Emmy was one of the most brilliant mathematicians of her time. Einstein recognized this, several other people did, And she, like women at the time, had a difficult time finding a position, but she published a lot, she was recognized, and she was so good that not only did she publish major things in her own field, she also gave some additional advice and help and stuff to other people in other fields that weren't even directly her own mathematics field, and they appreciated all of that. So she really was a top-notch person. And one of the things she came up with was Noether's theorem in 1915. And Noether's theorem said if there's some kind of symmetry, then there has to be a conservation law. Now, you know, scientists are kind of generous about what they mean by a symmetry. I mean, we all know that this is symmetric, okay? This is a mirror symmetry, so if I reflect this one in a mirror, it looks like that, and vice versa. Okay, well, there are other kind of symmetries, more general kind of thing. For instance, if I do an experiment over there, and then I go and I do the experiment on that side of the room, that's a translational symmetry. If I go to New York, it's still a translational symmetry. And it turns out that because we have that kind of symmetry, that requires conservation of momentum. If I get the same result here as I get over there as I get in New York, that requires conservation of momentum. I do something today, and I do something a week from now, time later. If I did it a month ago to get the same result, that requires conservation of energy. That's kind of a symmetry in time, symmetry in translation. One requires that you have conservation of momentum. One requires that you have conservation of energy. So those are really powerful tools that help you see how things flow out of the information that you put together in one area. It has a broad impact very often in other areas. Okay, we're going to go away from special relativity now. I know it's a quick trip, but that's unfortunately the way it is. We're going to talk about general relativity. And general relativity, Einstein did his thing, his big paper was in 1905. I think he didn't leave the patent office until about 1909. Finally got a position that he was willing to accept. Patent office was a good deal for him because he had weekends and evenings free and even some time to think about during the day, and he had some friends there to knock ideas around with and so on. And he said that one of the glorious thoughts that he had at one time, just before he left the patent office, was about what led up to general relativity. And he said, I was thinking, and if you're in an elevator in space, and it's a closed box, and you're pulled down on the floor, how do you know whether you're being pulled down on the floor is because you're sitting on some planet and it's gravity pulling you down, or you're out in free space and you're accelerated at 1g? You can't distinguish. And by putting those two ideas together, or that idea, he was able to come up in 1916 with general relativity. What that basically means is that space is warped. If you take a large mass, like our sun, it warps the space around it. And you can see that our Earth, then, is kind of in this, you know, it's down in this puddle or this little dip, and so it's just kind of going to roll around here, and there's no friction involved, so it just keeps going around and around and around. Now light, remember, is made up of photons, and these go through space. Well, if space is curved, it has to follow the curve. So it's a straight line, it's this least time, but it's curved, so it has to follow the curve. Well, what that means is this light from over here goes through the dip and comes over, and we might see it from Earth, and that gives us a way to measure whether this is actually happening or not, because when we look out, we think that the star is over here, or over here, and whenever we're over on this side of the sun, we can look more directly at the star, and we can compare the positions of the star from here and the positions over here, and then we can measure the warping of space. And that's what confirmed Einstein's general relativity theory in 1919, right after World War I. So there's a lot of confirmation for that. Can't believe that. Practice, you got to do some practice. And straight lines are relative, and I think we're all a little bit familiar with that, and just help give you a little bit of an analogy. You know, if you're talking about a straight stretch of the Portland Marathon, it's just right straight down the street. If you're talking about going across by airline, shortest distance in the surface of our globe, it's curved because airliners don't fly through the Earth, so you define straight line a little bit differently. Same thing whenever you're talking about curved space. So it's basically this kind of a thing. A straight line is a curved space. Is curved in the Euclidean sense, but it's really the minimum. And what that means is that if we have some gravitational thing here, we can have a large bend along this curved space for the direction that photons come from. And as a matter of fact, that's exactly what we see whenever we use the Hubble Space Telescope to look out at some of these distant galaxies and clustering and so on. So all of these blue pieces around here are focused from some galaxy or galaxies back in the distance by this group of clusters here, which is a tremendous amount of mass. And I talked last time, or a couple times ago, about dark matter. This also lets us get a view of what the dark matter distribution is throughout the universe also, if we have enough of these. Because, see, I can find out whether this piece associated here is associated with this piece over here or this piece over here, and maybe there are 3 or 4 or 5 different galaxies distributed behind there, and I can just sort them all out by looking at the photons coming from each and find out, oh yeah, those photons are the same as these photons, so that's the same galaxy, and these are a little bit more redshifted or not, and so on. So I can sort that stuff all out. Very complicated problem, but graduate students do that, so it works. And it's just sort of more diagram of the same kind of thing, so that whenever we look out toward this mass of the galaxy that's bending, that kind of focuses, we see 2 spots of light from this galaxy, or quasar, and if we see another one, then we can see these here, and as I said, we might be able to identify them because there's a difference in the quality of the photons that come from each one of them, and the more that we have to work with, the more complicated it gets, but the more information we can get from it. So there's a lot of neat stuff that can happen. This is the kind of thing that you would see if you just had a plain Einstein, and you put a heavy mass here to distort. The further you get away from it, the less distortion there is, but as you get very close, that's where the deep dip is. So the space is really distorted quite a bit when you get in close to a big mass. One of the other things you might think, well, suppose I have a flashlight, and this is very schematic, folks. Suppose I have a flashlight, and it's on a curve. Well, we know that the inside of a curve isn't as far as the outside of a curve, so maybe this goes 100 miles, and this goes 90 miles. But we said light always goes at the same velocity. And it turns out that this one goes shorter, it's the same beam of light, it's sending out the same photons, but when it's closer to this large mass, this is not Earth, this is some really big mass, and what happens is that, in fact, this tells you that if I go here for 100 miles in 10 seconds, and this is just, picking numbers, I hope these are right, and this one is 90 seconds, you still get 10 miles a second, 10 miles a second, but notice, the 90 miles only took 90 seconds here. Time moves at a different rate in a large mass. Did I get that
That should
right?
be 9 seconds. 9 seconds.
Thank you. I'm glad to see you're on your toes. That's what I really so anyhow, what it means is that the clocks run more slowly in a gravitational field, which is why here on the surface of the Earth, the clocks are running slower, just a tweak, compared to the satellites that are going around the Earth. Now, that may not mean an awful lot, because we're really kind of extremely small fractions of a second. But if you're running a GPS system, and you want to know where you are within a few feet, that makes all the difference. And so we have to be aware of what all that is that's going on. If this were, for instance, Jupiter, if we cut a hole a few meters across inside Jupiter and we put a watch in there, that watch is running at 1/4 the speed of a watch that's on the surface of Jupiter, because the gravitational field inside is tremendously larger than on the surface. So you can see big differences in speed over time, depending on where you're at. And this is what I mentioned. One of the other aspects that goes with this is that not only does mass warp the space, but if it's rotating, it also drags space around with it. Now let me make a little aside here. We generally think that just like matter is made up of atoms, little pieces of stuff, we also think that space is made up of little pieces of space, and time is made up of little pieces of time. Pieces of time are about 10 to the minus 43 seconds, and pieces of space are 10 to the minus 32 centimeters. I think that's right. And you would think, well, gee, if it's pulling stuff around, we ought to be able to measure it. And as a matter of fact, there's a satellite going around Earth now. Earth's not really a very big mass, but it should be able to drag something around that would be measurable. And in a couple of years, we should be able to tell whether or not this is another confirmation of whether general relativity works or not, because it says that rotating Earth should be dragging space around, and we'll be able to make a measurement of that. The reason you're worried about that kind of stuff is that maybe it's not dragging it around. Well, that gives us a niche to go and burrow into to find out, would the right theory be that? So all these little details you try to chase down so that you can find out whether your theory is right, or if it's not, where it goes wrong, and then start to understand why it went wrong. But this, so far, we see this in other places, and it all looks from those photons that come. We see the way that they're shifted around big bodies that are rotating, black holes and things like that. So I think that we expect that we're going to get the right answer even around Earth. And this is sort of more of a picturesque view of it. Here's the dip in the space warp, and the satellite's going around, and it's going to measure whether or not it's being swept around. One of the other things you always hear about black holes in science fiction, of course, is really big on this. You have a black hole, and anything that gets close to it gets sucked in, loses all its information, what it's made out of, and so on, except its mass. And black holes only are characterized by mass, a charge, and the angular momentum. Okay? When they fall in, they have an angular momentum, they get sucked in, and they bring in their angular momentum with them. And of course, that lets the science fiction people say, well, if you have a black hole that's connected on this part of the universe, maybe it goes through a tunnel to another part of the universe, and that would be really cool. And of course, science fiction uses that all the time, because it means that if I'm here on Earth, instead of going 26 light years around the universe to get to the star Vega, I just take a shortcut through wormhole. Dr. Nemo, or I don't know, there were some people that did that kind of stuff. And as far as I've heard so far, first of all, black holes are not stable, as far as we can tell. And whether the complexities are really difficult. And also, since we don't know a lot of details about how quantum mechanics and general relativity work together, and this is a very small warped part of space really crunched down, so quantum mechanics has got to be involved, and we don't know how to marry those properly. So the equations are kind of flaky, but it looks like they're not consistent, so we can't really depend on them. Here's sort of a general kind of thing that is kind of interesting. Matter, how much matter and energy also, because E equals mc squared, energy and matter tell space-time how to curve. And once you've got that curve, if the mass is moving, space-time curvature tells matter how to move. So the sun and the Earth set up a certain twist to space, a curvature to space. Once that curvature is there, the Earth is moving, the Earth knows how to move because it's moving in this curvature. So it's a sort of a back and forth combination that seems to really work. Good way to think about it. We are still confused. So now we're confused about much more important things. Now you got straightened out about some of that mathematics I had on the slide. So let me also mention just briefly gravitational waves, because as these things are moving around, in order for that information to get out to others, in other words, our sun could disappear, and we wouldn't know about it for 8 1/3 minutes. That information has to get out to us in some way. And just like photons, gravitons operate, and they travel also at the speed of light. And as a matter of fact, I brought along my local graviton with me. Here's a gravity wave. And since gravity doesn't have an anti-gravity, it doesn't have the other charge. So it's not like like a photon with electrics. Positive and negative charges create the photons. So gravity waves are different. They move on like this. That is, the space gets squished here, and of course goes up and down, and it moves along like this. So the next time your grandchildren are working with one of these hula hoops, move it up like this and tell them about gravity waves. Oh man, Grandpa, that's really cool. Or that's really nuts. So anyhow, we have one of the biggest and first gravitational wave detectors in southeastern Washington. It's near Hanford. It's in Hanford nuclear, big area. And this is about 4 kilometers long, And this is about 4 kilometers out this way. And there's also a 2-kilometer thing that looks like this. And at the end of these, there are 2 mirrors, one at this end and one at this end, and it reflects light back and forth, laser light back and forth for a while. And if these mirrors move in or out a little bit, we can detect that. And the sensitivity just blows me away. They have been running for the last 1.5 years or 2 years maybe, and now they're shut down partially so that they can upgrade, hopefully getting another 2 orders of magnitude. Whenever they get up online and really running, they will be able to measure, for instance, equivalently between these 2 mirrors, it would be equivalent to measuring the distance between here and the nearest star 4 light years away to within the width of a human hair. I mean, it is mind-boggling. And now they have to be about 100, in fact, or worse than that, so it's 100 human hairs, okay, about that far, between here and the nearest star. It's incredible. They haven't been able to detect any gravitational waves yet. Also, there's a slight one down in Louisiana, because, you know, if you get some result here, you're not sure whether it was just a burp or something, because waves crashing in on the, they have to isolate it from the waves crashing in down at the coast. A truck rumbling by 20 miles away, airplanes flying overhead, pushing the atmosphere down, had to isolate from all that kind of thing. It's incredibly sensitive. And also, things like this are being built in Italy, Germany, Japan. It's a big, big thing right now. This is the 4-foot diameter vacuum tube that goes along this, and the other one runs out here. I've visited there twice. The first time was kind of fun because you could actually go inside and get your booties, and you walk in and you go through and you see all this neat stuff. The second time was a year or 2 later, and they just kept you in the auditorium because they didn't want you in there to fool around and contaminating things. And they just gave you talks and so on. It was kind of interesting, just the scale of it to see the outside, but not nearly as interesting as when you can get inside. So let's take a quick break and see if we have some questions. And then, yeah.
A friend and I were talking about the twin paradox the other day, the kind of thing nerds do for fun. We ended up having an argument because we disagreed about the age the space traveler would be when he returned home. Say he was 20 years old when he left, and he went out for 20 years, like you were saying, and say it took 20 years to get back. My belief, based on what I've learned, is that he would be 60 years old on Earth. My friend said, no, as soon as he lands on Earth, he earns this, and this he said he learned in college physics class, that as soon as he landed on Earth, he'd be in the same temporal space that his twin was, theoretically, and would die because he'd be over 3,000 years old.
The physics professor that taught him that was totally incorrect. In spite of the fact that I messed up some arithmetic, it is in fact true, because he has undergone these accelerations. He's gone through space at dramatic speed, so his movement through space changed the way he moved in time compared to the people back home. So you're right, he's 60 years old, everybody else is dead and gone and 60,000 years ago. So.
Let's take
we have a question.
Thank you, that's very interesting. I understand what you said about a quarter or something. What I think is important is for us to understand there are no constructive absolutes anywhere. Absolutes are dangerous. The human hair, the hair you talked about, that's important. To come away from these things in any part of science with a sense of total understanding is an illusion.
Oh, and that's why I put up that thing initially saying that we just are hoping that we're getting closer and closer to reality and what's out there.
And that's why we're all here, we're all agnostics, right?
I'd like to remind
Even about science?
I'd like to remind people the purpose of this time is to ask questions, not to make statements.
How many more questions?
Just one more maybe, and we'll move along. We'll have other time for questions. Yes.
Well, I'm bothered by the idea that a cell or the body has its own time clock. And so while all of these physical things are happening, what makes the body suddenly have a different time? So that its cells die or decay at
Everything in your body, every atomic function, every molecular function It's not like you have to have a clock on the wall to tell time. It's just intrinsic. All the atoms go slower, relatively speaking. All the biological functions just go slower. That's why this guy is able to go out there and be only 20 years older. And all his biological things. He doesn't have any more wrinkles or anything than he would have just an additional 20 years. That's the real world. And if it weren't, you would end up with all kinds of inconsistencies and stuff. But it really is true. I mean, it applies to all the biological and everything. So, okay, let's hold it off until the end, because we might have some more that come up with quantum mechanics, but we can deal with it then later. Okay, let's talk about quantum mechanics a little bit, because if you think that this was a little confusing, what I'm going to talk about in quantum mechanics is, I'm not going to explain so much, it's just sort of tell you some weird things that are happening. I'll try to explain a little bit and even give a demonstration here, but we'll see where we go with that. But remember, I can't believe that. Well, take a big deep breath. You got to practice, 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 believing those impossible things. These are the guys that really put it all together. After Einstein said things are quantized, there was a lot of work to be done about how that applies to all the different areas of physics and so on, and the different things. And these three fellows all four got Nobel Prizes for one aspect or another of it, and came up with this information. That's back in the 20s.
Looks like Schrödinger took that long trip. Yeah. Looks like Schrödinger took that long trip. He was born before he died.
And there are two people now that in the more recent time that have been very big on that. Einstein, because he was skeptical and really never believed quantum mechanics. He thought there had to be something a lot more than that. We know something, but he came up with some very good questions that caused challenges and gave rise to some interesting experiments that I'll talk to you about in just a minute. And Richard Feynman is quite the guy. He got a Nobel Prize also for his quantum electrodynamics, and I'm a big fan of his for a variety of reasons. One is the physics, but he also was really kind of an interesting character as well. And if you haven't read, surely you're joking, Mr. Feynman, it's a book worth picking up from your local library or whatever and reading. He played bongo drums. He's the guy that really queried about the Challenger explosion, about putting the gasket material into the ice water on his desk and pointing out that it lost its flexibility. He was the guy that gave an independent report of that cover-up of the whole thing, sort of, like politicians typically do. Interesting guy in a variety of ways. And I can talk about him later if you want to, but I don't want to spend more time with that. Basically speaking, if somebody says they understand quantum mechanics, they really don't know what's going on. That's probably true. And that's Feynman. And one of the earlier guys, Niels Bohr, said anyone who is not shocked by quantum theory hasn't understood it, because it's really different from our daily understanding of the normal world about us. I already talked a little bit about photons, so I won't spend a lot more time. They're electromagnetic chunks of energy, and light is made up of large quantities of photons, and there are other photons also. The characteristics they have, they travel at the speed of light, they have a definite wavelength and a definite energy within the uncertainty principle that we'll talk about in a little bit also. They have a definite momentum, and they have no mass. Okay? So now we're going to talk about quantum mechanics. Energy is quantized, and I'll come back and talk about these a little bit more in detail individually, but let me just give you an overview. Things have both a particle and a wave character. There's a limit to the accuracy of measurement, and that's intrinsic. It's all probabilities, all the way down, and interactions are non-local. And we'll deal with some of those in just a bit. Some say it's necessary for the existence of science that that the same conditions always produce the same results. Well, they don't. Richard Feynman. And says, for instance, very simple example, light coming through a window. We see it now. Well, what's really happening? Remember, light is made up of gazillions of photons. And these photons come down. Now this is each individually has to interact with that window. And if we have a window that no window transmits 100%, okay? So suppose we have a window that transmits much less, and you're going to have some that's reflected or perhaps absorbed. And For instance, we do an experiment and we run 9 photons through a window. And it's about 80% transmission. Well, maybe the first one gets through, the second one doesn't, all these do, the 7th one doesn't. Okay, we do the experiment again. Now, if everything happens always the same, we ought to get the same result, but we don't. Maybe it's the 3rd one gets absorbed and the 9th one. And we do it again. And we do it again. And maybe on this one, maybe it's the next one, they all get through. But on the average of gazillions and gazillions, it's 80% or whatever the number is that it's transmitting through light. So every time you do an experiment, it doesn't necessarily mean you're going to get the same answer. The reason we tend to see the same answer is because we're averaging over tremendous numbers of activities that are going on. But quantum mechanics is basically probabilities of things. It's a direct challenge to causality, because if you don't know exactly where things started, we know the present, we can calculate the future, but quantum mechanics says we can't know the present exactly, because you don't know exactly which photons. We'll get to another example where you know even less than that, but you don't know which photons are going to be coming through, so you don't know exactly what the present is going to be. Now here's another thing that's kind of interesting and important, and don't let the formula scare you, I'll show you in just a minute. It basically says, and this has to do with some very general principles, again going back to symmetry, but it's the same kind of thing I talked about, conservation and so on. Well, this was realized in the 1920s, that if you had certain characteristics in the equations, then you had to have an uncertainty principle. In this case, a small change in energy and a small change in time, the multiplication of those two together has to be a very small number. And let me illustrate a little bit more what that could be. For instance, the electrical power used would be energy in your house, okay, and a time period, pick a number, week, month, I chose a month, make it reasonable. And if I keep that less than 1 kilowatt hour, suppose I say 1 kilowatt hour is a small amount, and I can scale that up or down however I want, then that could be a possibility of 10 100-watt bulbs running for 1 hour, or I could have 1 1,000-watt bulb for 1 hour, or I could have a 5,000-watt heater running for 12 minutes to heat up the bathroom, or I could have a 60,000-watt welder running for just 1 minute, or I could have a 1,000,000-watt short circuit for 3.5 milliseconds. So the whole point is that all of these things satisfy this equation. I don't know which one it might be. Could be any of these. And the importance of that is, let me give you a little bit more background. E equals mc squared. So we can talk about masses coming into this equation now also. And an electron has an energy, a mass, equivalent of 511 electron volts. That's a measure of energy. And creating an electron-positron pair requires 1,022,000 electron volts of energy. What that means is that I could, right here, create out of nothing an electron pair, charge conservation okay, momentum, all that kind of stuff okay, as long as I do it for a short enough period of time. So it's in and out of this vacuum. Nothing is there. I could also do it with protons. A lot shorter time they have to stay, but I can't tell the difference. And as a matter of fact, they are happening that way all the time. They have an effect on us, and we have to be able to calculate them. So in empty space, this is what you see happening all the time. And we have to take into account the calculations of all of this stuff because it has an impact. And if I have time, I'll go into that a little bit more later, but I don't know if I'll have time for that. The same is true also for momentum and position. So if it has a certain amount of momentum, mass times velocity, I can measure it, either its momentum very accurately or its position very accurately, but I can't do both with infinite accuracy. So that's another reason why you can't tell exactly what the present is, so you can't tell what the future is going to be. We know the present exactly, we can calculate the future. It is not the conclusion that's wrong, but the premise. That is, we don't know what the future is accurately, so we can't predict the future accurately. Now we're talking about really accurately. Remember, practice, practice, practice. Okay, we're going to do a double slit experiment because this is one of the basic fundamentals of physics that kind of gets across the idea about quantum mechanics being kind of difficult to understand because it's totally different from what we see in our everyday language. Energy is quantized, we know that, we know photons are chunks of energy, and the interaction is non-local, which is the thing we're going to notice here. If we have, for instance, and let me just talk about water, for instance. If you have a water wave, a water puddle, and you drop in a rock, it sends out some waves. And if you have a barrier here, a wall of some sort, with a little hole in it, some of that energy gets here and it starts bumping up and down here, and it sends out its own little thing of waves. And this is, I don't know if that's drawn well or not, but that's a vertical sheet, and I'm going to take a look here and see how much interaction there is. And I'm going to measure the height of that interaction by, and plot it on this vertical wall. So I can also consider that this is a light that's giving off photons, and the photons have a wave character, and they also have an energy. And that energy, whenever it's accumulated, has to be all given at one place at one time. It's not distributed, it's all definite amount of energy, and you absorb it in a counter or whatever, definite amount of energy. But how do we know where that energy is going to be deposited? Well, that has to do with probabilities. And the most effective way to think about this is these are really waves of probability, not waves of electromagnetism, but waves of probability. And so as we go here, it has a probability of being equally in any direction. And then we get to this point, and now it tends to go in this direction because it has some momentum, it tends to go that way. There's some diffraction, some complicated things, but it's going to end up giving you a little pile here where you have a splat and the photon is recorded there on a piece of photographic film or whatever, and you get a couple more, and you know, you get a distribution a little bit because of the probability distribution that you have here. And now if you did it a hole down here, you'd expect to see the same thing. Now what happens, however, if I have two holes? You might expect that you're going to get a little pile here and a little pile here, but it gets more complicated than that because you can see that the probabilities overlap each other, and it turns out they add up. Okay, so we end up getting a very complicated distribution like this. It's calculable. I'm sorry I didn't draw it as well as, you know, nice and symmetrical as it should be. But what happens is you start putting out individual photons, and they bounce around, and you would think you wouldn't see any photons here because it's totally blocked by a barrier. And the other conundrum as we go along here is that, okay, it's got this distribution, but if I cover this hole, I just get the little pile, or if I cover this hole, I just get the little pile. But wait a minute, this is a chunk of energy. You would think it has to go through either one hole or the other. But it doesn't. It knows where things are, although all the energy has to be dumped at a particular place when it finally hits the screen and makes a record on that thing. And the probability distribution is what is here, and it shows up. So it's all probabilities. It's all kind of strange, and it kind of understands the whole stance. Now another thing I sometimes use as a demonstration is, for instance, if I'm in our conventional wisdom, if we're in a room and there's a fly flying around behind me, I know, I can hear it, I know he's there, and I see all that stuff. In quantum mechanics, there's a probability distribution. When I turn around to look and see where he is, I can find out where he is. But until I turn around and look, it doesn't make any, I don't know. But the thing is now, suppose I take a chair, and I put a chair there, and in our real world, the fly has to go around here, and has very little effect about where the fly is over on the window or whatever. But whenever I put that chair there and it's a quantum mechanical situation, that chair changes the probability of the fly being wherever in the room. Just to the fact that the chair is there, even though the fly's not anywhere close to it. Now we're talking, when you're talking flies, you're talking about interacting with material, and that doesn't work. It's got to be some unencumbered thing, uninfluenced by the surrounding. But anyhow, that's what happens. The probability distributions really determine how the photons are going to be distributed along this screen. So it's really quite different. And it does, without understanding how this is working, the fact that you have that second hole does impact on where that distribution of photons is going to be along the screen. Electrons also have a wavelength that's just much, much smaller than photons. They have an energy and so on. And actually, I've done this in a lab, and you really need a much, much finer screen, so you use crystals to give you this distribution, and you diffract them. Okay, so it's another one of those practice, practice, practice kind of things. Now, let's go to a rather interesting thing, and I think we have plenty of time to do this. Polarized light. You all have those polarized glasses to get rid of the reflections and so on. Now remember, a photon is a chunk of stuff. You can't divide it up. So it's either all or nothing in a certain way. And photons, when they're moving along, if you have photons vertically polarized, the electric vector is going up and down like this. Okay, and it's traveling at the speed of light. I have to wait for this. I don't know how fast I can make this work. And if we do it horizontally, we can do the same kind of thing, and we have it polarized horizontally, and then the electric vector is going back and forth horizontally. So now, that's kind of, well, okay. If, for instance, you had a bunch of sticks, and you had a fence, and the sticks were just kind of randomly distributed by their orientation, you're throwing them toward this fence, you would think that not too many are going to get through. Okay, most of them are going to end up piled down here, maybe only a couple of percent, even though they're randomly distributed, only a very small percentage is going to go through. And if I put my fence horizontally, the same kind of thing is going to be happening. They're going to go through, and you're going to end up with ones that are vertically up here and horizontal here, but most of them get stuck down here because, you know, very few are just that percentage. But that's not true with polarized light. See, if I have a polarized filter here, and I have a light here that's, say, a hot filament light, there's no particular polarization associated with the light, just randomly given off. And as a matter of fact, they don't have any particular orientation whenever they come off here. We don't know what that orientation would be unless we start to make a measurement. So we have the light, and I kind of schematically show it this way. And after it goes through this polarization filter, the photon has to choose which state it wants to be in. Either in this state, where it goes through this filter, or perpendicular to that state where it gets absorbed. Okay, it can't go in between and part way this way and part way that way, because it's got to be, it's one chunk of energy. It's all the same. It's got to go one way or the other. And whenever it gets polarized here, half gets transmitted. This polarization filter is in exactly the same orientation, so it all gets right on through. No problem. Okay, now if we do it this way, so that now I still have the same polarized filter vertically, when it gets to this other one, now it's already in this state, but it's blocked completely. So it doesn't get through that. Now, the interesting part comes here. Suppose that we have polarization here, polarization perpendicular to here, so we know nothing is going to go beyond this. Suppose I stick another polarized filter in the middle at 45 degrees or some other angle. So the stuff coming through here is vertically polarized. What's going to happen? Well, part of it gets through. Because now, this is vertical, and this is a different angle, and it's not at the angle that's going to be blocked completely. So it's possible that it can populate this other state in a different way. And it depends upon the cosine of the angle, cosine squared of the angle. So depending on what the angle is, but if we have it at 45 degrees, it's going to be half. And as a matter of fact, then that gets through, and you'll find that, in fact, there is some light coming out here. Now, it just so happens that I brought along with me a ring stand, which is actually from my chemistry set when I was in high school. And this is from my basement from a long time ago, and we're going to try to do an experiment down here. Maybe you can put up the target over there on the wall. And I happen to have 2 Polaroid filters from camera filters and stuff. And the only other one I could find is a pair of sunglasses, but that also lets you know that it's everyday stuff, you know. So we'll get to that in a minute here. Brown tape, essential. Also, there's always a danger in this because, you know, the general way that they distinguish the different sciences is, if it's slippery, it's biology. If it stinks, it's chemistry. And if it doesn't work, it's physics. So, we're going to do this. It worked before. They all say that.
Would you explain first what it means to be polarized?
The electric vector is in a definite direction. And whenever we have it vertically polarized, the electric vector is like this. And whenever things reflect off, they're polarized this way primarily, which is why in your glasses, the polarization vector will be like this, so it blocks out the part of the reflection that's horizontally polarized. Okay, so now, if I shine this through this Polaroid filter, it can hit that, and you can see that there's quite a bit of light there. Okay, so now I'm going to try to take this other one. Okay, so now what I want to do is I want to move this through here, and let's see, I come up there, and if I can pull this, oops, got to get my hand out of it. And now I'm going to rotate this until it disappears. Okay, so now it's out. See, I rotated it so that it disappears. And now I want to take that into position like that. Okay, so we have now kind of a delicate thing here, but it's sort of, you can see it very faintly. I didn't get it quite exactly right perhaps, but it's there. And now if I take my other Polaroid thing, and I put this all together, and I'm going to get that in there, and I rotate that. Let's see if I can get this all lined up here someplace.
Well, it's physics.
I was hoping it was going to be quantum mechanics. Let's see if I can do this. I'm amazed how nervous I am about this whole thing here. If somebody come up and just hold this, no, I don't. It's not the glasses. It's that I'm getting too nervous. Okay, just press the button and point it through that. Oh, there it is. You're right. Okay.
But this side of the audience can't see it because it's just too
Okay,
far
there. See,
away.
it gets brighter and dimmer. There it is. Okay, we finally got our act together. Thanks very much. I'll sell it to you cheap. Okay, so that was another quick thing. Anyhow, there is some that gets through because we have that material. I'll be a little more careful about demonstrations like that. You should be able to believe that now because you saw the demonstration. Interactions are non-local. This is another one that's kind of interesting. This is the entanglement Einstein-Dulski-Rosa. This was suggested by Einstein in the middle of 1930s. He and 2 graduate students put this challenge because Einstein never really believed in this spooky action at a distance. And the idea is that we're aware of the uncertainty principle. You can't tell exactly where things are here, exactly where things are here. So what he suggested was, suppose you take 2 particles, and they might have a certain angular momentum or whatever, and they're out of contact with the real world. That is, you can connect them, but you don't do anything that's going to disturb them or give you information about what their situation is. And you set it up so that they blow apart then. And presumably somebody down there will decide he's going to measure very carefully where the position of this one is as it goes past. So he gets that infinitely accurately. And the guy on the other end is going to measure the momentum very accurately, okay? So now, you know, where I said there's a limit on the change in position and the change in momentum, that has to be below some very small number. Well, if I get this infinitely accurately over here for position, and this one infinitely accurately over there for momentum, then I got the whole schmear because of the symmetry, okay? It turns out that as soon as I make a measurement over there, no matter how far away it is, the other one instantly knows about that and acts accordingly. This is that spooky action at a distance, and the most recent measurement that I saw of it, in fact, was made over in the Canary Islands, and they used photons, and they separated them by 135 miles. They've done a lot of things in the local laboratory, and they've expanded distances, and now this was done just 2 or 3 years ago, 135 miles. But there's no reason why that can't be across the universe. That's something we really just don't fundamentally understand. But instantaneously, not speed of light, instantaneously, this one over here changes in such a way that all the things work properly, the conservation laws and so on. So that's really the spooky action of distance really is true. They're using some of those kinds of things for trying to build quantum computers. The big problem is that you have to keep these things isolated, so it's very hard to hold them in any way without disturbing their state. As soon as you disturb the state and they have to force themselves into one state or another, then you've lost this entanglement characteristic. So you need to preserve that. And that's why it's a lot easier to do it with photons than it is with a lot of other things. So this works well with, and it's easier to do with photons. They started doing that now with a couple of simple single atom things that they isolate and hold in very cold magnetic suspension or situations. But that's pretty much just the way it works. So that's pretty much the way it is. Let me just go through one more thing here, and that actually finishes up everything that I have. Now, I mentioned, suppose we have a charged particle in here, say it's a proton, electron, whatever, and I told you all these things are coming out of the vacuum, and they can be out there for a while, and then they go back, out for a while, go back. As long as the time is short enough, you can have tremendous amounts of energy, big particles, all kinds of things can happen. Well, if I have a charged particle here, the things that come out of the background, and I'm going to be outside this at some distance, okay, a distant observer. Whenever they come out like this, because of the charge, they're going to orient in such a way that the charge takes this into account. That means that this distant observer out here sees the charge here modified by all of the stuff that's coming out of the vacuum, back in, out of the vacuum, back in. So you don't really get a good idea of what the real charge is. So if you really want to know what the charge is here, you have to renormalize. So you drop that out at your next cocktail party and say, yeah, well, I realize they have to renormalize the charge of the electron before revealing what's there. I said, yeah, these are really scary. So those are the kinds of things that people have to worry about and be considered about. This is just a further demonstration of that kind of thing. Anyone who's not shocked by quantum mechanics has not understood it. This is just a summary of the stuff that I had before. It's all probabilities. That's probably the easiest part to understand. You know, photons coming through a window, going through a polarized filter. Interactions are non-local. And one of the things there that I guess I should make comment is you can't transfer information that way because it's all random. Whenever this thing gets set into a certain situation, you don't know whether it's going to flip up or flip down. Okay? It could be either way or any way. You make a measurement, polarized light, and it's going to be up. Well, half the time it's going to be up. The other half, you know, it might be the other way. So that means that whatever happens on the other end is just the opposite, but we don't know which it's going to be first. So it's totally random. So you can't transfer information that way, but it's instant. So that garbage, quickly over here, quickly over there. And that's pretty much it.
Two.
Long questions. Yeah, question here. So, this is all such strange stuff here. Michael Shermer in many of his books talks about how people believe weird things, and his theory that people have a knowledge filter, you know, in terms of figuring out what kind of stuff is just crazy ideas and what's real. My question to you, and is when people really start to study quantum mechanics and special relativity and things that seem to be so different from the real world, do you ever run into people who seem to lose that kind of knowledge filter? Because I know somebody who has a physics degree and knows all about quantum mechanics, but then I've also found out he believes in aliens and there's a space on the opposite side of the moon, and he thinks that the Earth is hollow and there's people living down there. So I'm just wondering, have you ever seen any kind of a correlation between people getting into this?
You ever listen to Art Bell?
Yeah.
And quantum mechanics and all that stuff?
Well, the thing is, I mean, one of the things I used to like about science fiction was that it sort of was based on science or reasonable extensions. Now a lot of this stuff is magical and all that, so I really got turned off on it. I think there's two different classes that I look at. There are those where, since we don't know anything, there are possibilities. And there are people that expand those possibilities into plausible or possible or things that are not ruled out. So there could be multiverses. There could be other universes parallel to us. There could be others parallel to us upon one of the additional dimensions that string theory talks about, and we can't see it even though they're right here. Maybe that's an effect of dark matter gravitationally through the two, because gravitons travel across some of these dimensions and don't. So there's all kinds of scenarios that are really weird and strange that are possible. And then there's the other stuff where some group of gremlins living at the center of the Earth influencing all our lives. like who is it? Sasquatch. And, you know, the number of Bigfoot imprints and so on. And then people come off a wall about it. It's like a built-down man, you know, it's a big facade and there's hard evidence, but it's a hoax. And there's just all kinds of, so you have to be a little careful. But one of the classes I had, some people came up to me afterward, had PhD and whatever, and he had written his paper talking about the real possibility of aliens. And he said, we've looked at all the different features of some of the best sightings, and we thought that they really are around someplace. And he said, you know, when you consider some of the things that we don't know about physics, it's possible that they might have possibly come here. Well, he's not saying he saw them or that this is a legitimate thing or whatever. He's saying it's possible. Yeah, okay, it's possible. I mean, I think I talked in one of the previous things. Why would they care? You know, if they're capable of coming over here and they're a billion years ahead of us, maybe they just want to look at us like we look at things in the zoo or something. But they're not going to communicate with us particularly. I mean, that's also, it's possible, but what I just said could be a whole bunch of things.
Right here.
Last question from Robert.
Is time always linear? Why not?
As far as we know, time is linear. And I guess if time wasn't linear, we wouldn't know it, because we're embedded in whatever time we're embedded in. But I don't think that the equations indicate that there's any reason why it should be, you know. There are reasons why time doesn't go backwards. Entropy and some other things, strong arguments. It could be there's another universe, and you know, there are some things, but it gets very, very stylized and carefully defined and so on. And the thing is, all bets are off for a lot of absolute answers because we don't know the full answer to things.
It would change things a lot, wouldn't it?
I'm sorry?
It would change things a lot.
Well, if we're embedded in time, and all we see is time, you know, all our biological things move up faster or slow down, I don't think we notice it. As a matter of fact, the half hour before this was longer than the half hour now, but we didn't notice it. All our biological things did the same kind of stuff, you know, we speeded up and didn't. Yeah, I don't know.